Back in 1944, Erwin Schrödinger, one of the legendary architects of quantum mechanics, asked this incredibly simple question: what is life? Now, he was a physicist, not a biologist, which made it all the more audacious. But his answer would end up changing science forever by tackling this massive paradox at the very heart of our existence. So let's break down his revolutionary ideas. All right, let's dive right in. The whole core of Schrödinger's book is this beautiful central paradox. You've got life, which is just a masterpiece of order and stability. But then the entire universe is governed by a law of physics that says everything inevitably breaks down into chaos. So how on earth does life pull off this magic trick? To really get Schrödinger's answer, you first have to see the problem through his eyes, through the eyes of a physicist. And what he saw was this fundamental clash, a battle between two cosmic principles: order versus disorder. So on one side, you have life. It builds and maintains itself with just stunning precision. But on the other side, you've got one of the most fundamental rules of the universe, the second law of thermodynamics. It basically says that over time, everything just falls apart. It becomes more random. Physicists have a word for this growing randomness: entropy. And right there, you have this cosmic scale showdown. Life is trying to build order while the universe seems dead set on creating chaos. Now, we tend to think of physical laws as these rigid, absolute rules, but Schrödinger points out a really crucial detail. They're statistical. They only seem reliable because they're averaging out the chaotic behavior of trillions upon trillions of atoms. The order we see in our everyday world, that's really just the law of large numbers doing its thing. He explains this with what's called the square root of n rule. And in simple terms, it just means the more atoms you have in a system, the more predictable their group behavior becomes. If you only have a few atoms, their actions are totally unpredictable. This is actually why our sense organs have to be pretty big atomically speaking. I mean, can you imagine if your eyes could see every single random atom bouncing around? The world would just be a chaotic storm of static. Order and predictability, they only show up when you have a massive crowd. Okay, so if the laws of physics need huge numbers to work, that brings us right to the heart of the mystery. Where in the tiny, microscopic world of a living cell does life store the incredibly stable instructions that create and maintain all its order? Well, the answer, which geneticists were just starting to figure out back then, is hidden inside the chromosomes. These tiny little structures in a cell's nucleus hold the complete blueprint. Think of it like biological software that dictates the entire four-dimensional plan for an organism, from a single cell all the way to a fully formed adult. And here is the absolute kicker. The gene, the fundamental unit of heredity that carries a specific instruction, is unbelievably small. Schrödinger figured it couldn't have more than about 1 million atoms. Now, 1 million sounds like a lot to us, but to a physicist, that's nothing. It is way, way too small for statistical laws to guarantee its stability. It shouldn't be stable. And yet, it is. For generations. So if it's not stable because of statistics, then what in the world is it? This is where Schrödinger proposed a brilliant, totally new idea. He called the gene an aperiodic crystal. Now, the analogy he used here is just perfect. Think of a normal periodic crystal. It's like a simple wallpaper pattern where the same basic design is repeated over and over and over. Boring. But Schrödinger imagined the gene as an aperiodic crystal, something more like a masterpiece tapestry by Raphael. It's still a solid, stable structure, but its pattern is incredibly complex and it never repeats. And because of that, it can carry a huge amount of information, a code. So Schrödinger had a theory for how the genetic code could be so stable, but the next piece of the puzzle came from a really unexpected place. It wasn't about its permanence, but about the very strange way it changes. You see, Darwin had this idea that evolution worked through tiny, continuous, gradual variations. But by Schrödinger's day, biologists knew that wasn't quite the full picture. The changes that natural selection really works on are sudden and they're discrete. These changes are called mutations, and they are, as he put it, jump-like. A gene is either in one state or it's in a different mutated state. There are no half steps, no in-between forms. For a physicist like Schrödinger, this distinct all-or-nothing behavior was a massive, flashing clue. And this illustrates that idea perfectly.
Genetic change isn't a smooth ramp you can slide down. No, it's a staircase. You take distinct, separate steps. And that jump-like quality immediately made Schrödinger think of his own field, quantum mechanics.
So if genetic change happens in these sudden, discrete jumps, what else in the universe behaves that way? Schrödinger realized the answer was right in his wheelhouse, the bizarre, jumpy world of quantum mechanics. You see, in the quantum world of atoms and molecules, things just don't change smoothly. A system can't have just any old amount of energy. It's forced to exist in specific separate energy levels, or states. It can leap from state A to state B, but it can literally never, ever exist in the space between them. So here's the crucial point, the big insight. The gene is a large molecule. Its incredible stability doesn't come from statistics. It comes from the fact that it's resting in a stable, low-energy quantum state, kind of like a ball resting securely at the bottom of a valley. And a mutation? That's simply a quantum jump. It happens when a random jolt of energy gives the molecule just enough of a kick to push that ball over the hill and into a neighboring valley where it settles into a new, different, but also stable state. And just like that, this one powerful idea explained everything. It explained why the gene, even though it's made of so few atoms, is so incredibly permanent. And it also explained why its changes, mutations, are these discrete, jump-like events. It's just the very nature of quantum reality. Okay, so quantum mechanics explains the stability of the gene. Fantastic. But that's just one molecule. This brings us right back to the big picture. How does a whole living organism keep its act together against the universe's constant push towards chaos? This is where Schrödinger takes his quantum insight about the gene and scales it up, providing this absolutely breathtaking answer for how all of life works. This is it. This is his most famous and maybe his most mind-bending statement. Life doesn't break the second law of thermodynamics. It doesn't defy it. It just uses an incredibly clever workaround. It survives by, well, eating negative entropy. So what on earth is negative entropy? It's just a physicist's fancy way of saying order. See, just by being alive, an organism is constantly creating disorder, or entropy, inside itself. To fight against this constant decay, it has to pull in order from its surroundings. We eat, drink, and breathe to consume highly ordered molecules. In essence, life is this little pocket of order that maintains itself by sucking up order from the world around it and then dumping disorder back out as waste. It exports chaos to stay organized. And why all of this still matters so much today is that Schrödinger's ideas were just astoundingly predictive. His aperiodic crystal, this stable, complex, non-repeating molecule that carries a code, was a perfect theoretical description of the DNA double helix, which Watson and Crick wouldn't discover for nearly another 10 years. He basically described DNA before anyone had ever seen it. In the end, Schrödinger argued that while life doesn't seem to break the laws of physics, it operates in such a unique and incredible way that by studying it, we might actually discover entirely new physical principles. And he left us with that thought, a powerful reminder that the greatest questions, the biggest discoveries, are often found not deep inside our own fields, but right there at the boundaries where they meet.